So let's kick off and start with what MSC Nastran is and then where it comes from. So MSC Nastran, there's an article that was published in 2011 about the first 10 companies, software companies that still exist today. And MSC Nastran was one of those companies. They started by developing the program Nastran. Okay, in terms of what MSC is though, MSC is a pretty large company, well over 1,000 employees sitting worldwide, lots of different offices you can see. And in terms of what the software is being used for, it's a pretty wide range with automotive, air and defense, and every industry being the largest, but by no means the only industries that actually use the software. In terms of the software that's covered by MSC Software, we've got acoustic simulation, additive manufacturing, self-driving vehicles, CFD calculations, detailed composite microscopic behavior simulations, design optimization, fatigue, multi-body dynamics, modeling, in other words, mechanisms, and so on. We'll see some examples in the background later on. Multidiscipline, simply meaning different kinds of analysis in one environment. Noise and vibration, nonlinear, automating processes, rotordynamics, simulation, product data management, structural analysis, and systems and control. So as you can see, it's a pretty wide range of topics, and most of these are part of one cohesive set of applications. So if you now look at what Nastran is, or MSC Nastran specifically, it's a powerful, tried and tested, it's industrial grade structural analysis, FEA Solver. It's the original, most widely used, most extensive, most trusted, most accurate, and so on of all Nastran versions today. And I'll mention different versions in a moment. So it's a multidisciplinary structural analysis software, meaning we can do statics, dynamics, thermal, and so on, quite a few additional ones from one piece of software. Okay, where it's being used and some comments from existing customers. So I'm not going to read all of them in detail, just highlight some sections of these. Physical testing normally costs $10 million to run, which you don't want to have to repeat. So the Nastran Rotordynamics code allows you to test it in a virtual environment. From Bombardier, it provides opportunity to make sure designs fulfill the requirements before you make it. Mahindra is the simplified process by using the Nastran embedded fatigue, enables highlighting these size dislocations and so on to make it easier effective. Ford, use of MSC software allows us to optimize the microstructure of designs. So what this refers to is using microscopic simulation coupled to something like Nastran to calculate the stiffness and mass behavior of the different parts. And then from BMW, the advanced optimization process are used on both component and system level. From Renault, they anticipate exterior noise by simulating the engine noise and then combining Nastran and Actran to predict what drive-by noise is expected to be. From AV, it's the correlation of the static wing load testing with MSC Nastran nonlinear stress model was so accurate that at first I did not believe it. Because as you can see, it's a pretty wide range of customers and all of them are pretty happy with the software that they're using from MSC Software. In terms of what MSC Nastran is, it's this one-stop shop for multidisciplinary analysis, meaning we can do things like linear and nonlinear analysis, statics, dynamics, thermal, buckling, Aero-elasticity, and quite a few more. So before, or if you didn't use Nastran, a lot of these you had to do in separate software, each specializing argument's sake in Rotordynamics or Aero-elasticity. In this case, we can do everything from one interface. Then Nastran being this comprehensive structural analysis portfolio. So basically, we have the different disciplines, statics, dynamics, thermal, fatigue, different ways of splitting it as well, linear and non-linear. But this is not the full picture. if you dig a bit deeper, if you look at, for argument's sake, I'm not going to go through all of them in detail. In dynamics, we've got linear and nonlinear, implicit or explicit for nonlinear. For linear dynamics, we can calculate things like natural frequencies, normal modes, damped natural frequencies, which is complex eigenvalue calculations. We can do transient and frequency and even random response calculation using either a direct time integration or a modal and then a time domain integration. Then some additional capabilities that makes a lot of these easier is things like ACMS, automated component mode synthesis. It's a method that is very efficient to calculate lots of modes on large structures. So we can sometimes calculate hundreds of thousands of modes on a really large structure and still do it relatively fast. Nastran can perform acoustic calculation, and it can couple to external specialized acoustic software like Actrin, for example. On the fatigue side, in an analysis, we can calculate the fatigue life directly instead of just reporting stresses. So in some instances, it's a much more efficient way to work. It doesn't completely replace the idea of solving the loads and stresses and then taking it to the fatigue software, because there's additional useful features that's available on those, and especially to do with if you have to change the design. There's lots of effort going into high performance computing, parallel processing, GPU, different solvers and so on. We also have optimization, lots of different methods, and there's some nice slides on that, so I'm not going to go into it now. And then for statics, we have linear and nonlinear, implicit, explicit, linear buckling, nonlinear buckling. There's thermal calculations, coupled thermal and structural simultaneously, and so on. So Nastran has a pretty wide range of applications that it effectively covers, pretty much getting back to the whole concept of multidisciplinary solving. Another way of looking at the same information is we break it down into linear, dynamics, nonlinear, fatigue, optimization, and so on. Then all of the different subcategories that forms part of it. So for linear, we may look at statics, buckling analysis, modal analysis, Aero-elasticity, and so on. So all of these are available in Nastran today. All of them share this common data model, meaning it's the same elements, same material, same properties that you have to define for most of these. There's exceptions, like if I want to run plasticity, there's additional information that I need to define. Same goes for fatigue. There's additional material properties that we have to define for fatigue. But the rest of the behavior stays pretty much the same. If you've ever heard of the term Nastran and wondered about what the difference is and whether they're the same, yes, they kind of started out the same. In 2002, the MSC Nastran source code was shared. It had to do with court cases and stuff. And there's a couple of companies that effectively bought the right to use the source code. That was in 2002. From then on, every one of those developed on their own. So this is just an example of some of the features that was added in MSC Nastran. So effectively, it means not every MSC Nastran compared to difference is not exactly the same software, even if they started and shared a lot of commonality initially. Okay, so there's a lot of functionality. It's now more than 17 years already since then. It's now 23 years, I think. So a lot has been added since then, and we look at some of just the latest changes that was made towards the end of this presentation. Okay, then MSC Nastran, it's an industry-ready FEA solution, and it's been used for a wide range of applications. So if you look at the different kinds of analysis, again, linear analysis, dynamics, nonlinear, and other analysis types. And these are not exclusive. There's actually a couple of additional ones, but these are the important ones. I just want to stand still a moment by looking at specific features. If we talk about the Nastran Solver, I think they usually refer to this as 1.1. You can also call it 101 if you want. This is simply an internal reference with an ID that says this is linear statics. Do you need to know these? Not really. There's only two that we typically know really well. 101, which is linear statics, and probably Solve 400, which is the more advanced nonlinear solution sequences. So we'll talk about solve for towards the ends of this as well. So don't worry too much about if you see a number or a solve. It's simply a different way of saying it's a certain type of analysis. If you scan through some of these, we look at linear analysis examples. So what is it? Well, linear is pretty much the bread and butter of most structural engineers, where we assume that stuff is linear. And, for a large category or group of analysis types, it makes perfect sense. We don't want it to go plastic unless there's contact. There's nothing special there. Only other possibilities, geometrically nonlinear, that usually has to do with thin plates with some kind of a pressure load on top of it. It's oversimplified, but still. So it's very efficient to run something linearly with only if it is. In terms of the Nastran features, it's really accurate, consistent solutions, one of the most trusted software to get the answers out. There's some useful diagnostics if something goes wrong. And if you then later on need to run anything else, dynamics, nonlinear optimization, you've already started with a model and you continue in the same software. If you look at nonlinear, well, most of the real world is nonlinear to some extent. In some cases, it's very mildly, which we can approximate as linear. But there's cases that's extremely nonlinear, and for that we need some kind of nonlinear analysis. We also have the distinction between static and dynamic nonlinear behavior. So for statics, if I have this clip and I do it statically, I'm slowly moving it in and I'm only finding the steady state solution. If I want to see that thing snapping in, that'll be a transient solution. So one thing that's different to solve 400 compared to pretty much anything else, in all the others, we run argument's sake static or steady state heat transfer. In solve 400, every subcase or sub-step, as it calls it, can be a different analysis. I can model a sequence of events, whether that's a manufacturing process or something like in the first step, something's overloaded, it goes plastic, and I want to see what happens after that to the modes, argument sake. All of that is possible by running a solve 400 analysis with different sub-steps. So there's some smart defaults making it easier to set up nonlinear analysis. So again, this is stepping from the linear space into nonlinear. And again, there's some diagnostic information available. So the biggest advantage for Nastran nonlinear compared to anything else, even Mark from MSC, is simply you already know Nastran, so it's a bit easier to then follow and change and learn the new things for the new solution type. Just again, some examples of different things that we can simulate and then also the different kinds of analysis. I'm not going to spend too much time on this. So just the examples of static analysis, normal modes, and so on. Okay, then just some examples further on from buckling. So if you have some kind of a structure that we try to load, there's a very coarse mesh, but you'll see this buckling shape occur. Something like a submarine, its failure mode isn't so much compressive stress as it's buckling. So, and there's all kinds of ribs in there that stiffens it up, but at a certain pressure level, something like this happens. Now, this is something typical on thin wall structure or beams with a compressive load, for example. By no means exclusively. Here's an example of a Coke can that is buckled, and it's plastically deformed into that buckled shape. So it's possible to model effectively something like this using a buckling analysis, or even a nonlinear analysis with plasticity, you can get to that same final state. Response analysis. So some examples, if something spins, there's a radial load. We'll look at some of the other examples later on. So there's an example of a shaker table. So there's some PSD input at that location. We want to see how the structure behaves. Now this is a very coarse model. It shows the concept. Here's a much finer and probably more common kind of a model that customers typically run. In this case, it's a model with 8.5 million degrees of freedom. So I'd estimate somewhere around between 1 and 2 million elements effectively. And in this case, the frequency response, meaning we're solving it at a range of different frequencies for some given input. Okay, and then just a little bit of a comment in terms of performance. I've already said Nastran 2002 was shared. Even Nastran 2010, if you compare that to a more recent version, there's a significant speed up. So it's one of the things that MSC works on a lot between different versions, to try and get things done fast on the same computer. So some examples of heat transfer, we've got some kind of a component, so that's the mesh, and there you see the temperature distribution, steady state. We can also do transient that says, I'm heating it up, how will the heat transfer as function of time? In other words, if I pick a node or a location and measure the temperature, I'll see that varies a function of time. In this case, I'm interested in what the final temperature will be. Then in this one, I want to stand still slightly longer because we reference optimization here and there a couple of times further on. So in terms of optimization, there's quite a few analysis types, optimization types that we can perform. So some of the basic ones, if you do an optimization course, you'll typically look at design variables, how that relates to your model, and set up your different stress limits and displacement limits in terms of side constraints. And you've got some kind of a function, the weight function, that says it's the good or bad design. Now, a lot of that is partially pre-set up in Nastran. There's certain templates making it easy, but you're still able to model pretty much anything you're interested in. So just some of the common types, we have a size kind of analysis. I've got different plates, and each of these I want to optimize what the plate thickness for that part should be. So if you run analysis, you'll see these variables. At some point, you see they start to stabilize, meaning those final values there is pretty much what the thickness of each of those should be. A typometry analysis is something that I'm not certain if it makes too much sense on a card, but it's a great model to show it. Is for whatever layers you're applying, what should the thickness be in different regions of the part? So there you can see there, so it needs to be thicker in that part. There it's kind of a blue, so it can be a thinner part in that location. So this will probably be useful for initial sizing for a new design. We can also do shape optimization, where we're physically moving those node locations and rerunning the analysis effectively over and over. Well done by the solver, we don't need to rerun it. And we can get from an initial to a final shape that says this one passes all my required tests. The topography one is where no material is added or removed, but it moves these nodes perpendicular to the surface. In other words, we get these kind of creases formed. If you look at something like this, it's going to have either low stiffness in twist, if I twist about that axis, or if I look at the natural frequencies, these things will flap pretty badly. By moving these nodes, we're effectively massively stiffening up the structure without changing the amount of mass of that specific design. So obviously more expensive to make something like this than this. But in industries where we make hundreds of thousands or tens of thousands of a specific part, it may be worthwhile to invest in something like this. And then we've got topology optimization, which traditionally simply, I've got some kind of a space, I've got loads, and I want the software to tell me where material can safely be removed. Now, in the latest versions of Nastran, there's an additional option, the Neo solver specifically for this, and then it acts more like, if you know, the product generative design, where it'll end up with actually a smooth 3D printable shape or a part that you can mesh if you want to do a more detailed analysis afterwards. So it's similar to topology and it's highly related. And to switch it from the older method where you simply you remove elements, with this, it's simply one parameter that you need to activate to get it done. And then the second one is to say, how do you want that done in terms of constraints? Should it be castable, machinable, 3D printable, and so on. In terms of nonlinear examples, so some kind of a clip that moves in. So there's contact. There's another example of contact and plasticity, large rotations on some kind of suspension component, most likely. Parts that are moving in different directions at the same time or in or out of phase with plasticity and so on. So this is pretty much bread and butter for Solve 400, which is nonlinear analysis. Sol 700 is related to Dytran. It's not exactly the same, but it's close enough. So the intent is to run explicit analysis. If you're not familiar with implicit and explicit nonlinear, explicit is much more efficient per time step, but we're limited to very small time steps. So anything like a crash simulation or this fluid structure interaction where we need a very small time step in any case for that to rotate, it makes more sense in this. Now again, we can do the same simulations in Dytran that we can do in Sol 700. The difference is simply whether you're already comfortable with Nastran and want to continue, or whether you'd rather work with software that's just designed for that kind of analysis. Okay, then Rotordynamics is when things spin, it's really easy for stuff to start going wrong. So your natural frequencies change as a function of the shapes. And we get to the point where static loads start to excite and mode, something like this. So we've got a bearing with stiffness, that's why it moves up. As it's spinning, that load on the shaft is in different directions. So at some point, that static load of gravity is actually creating a load in different directions as this thing spins. But it's more complex. So there's the Coriolis forces and so on that's also taken into consideration. So the rotordynamic capability allows us then to solve these kinds of structures, but also to couple that with the rest of the structure to see how it interacts with the structure. So not everything has to spin, only certain parts. This can be done using anything from the simplest case, beam elements, to special axisymmetry elements, all the way up to full three-dimensional models, solid shells, and so on. And then something that's relatively new, still almost 10 years by now, is embedding fatigue inside of Nastran. So it's called NEVF, simply Nastran embedded vibration fatigue. Now there's also transient analysis, it doesn't need to be vibration only. So this says we've got a mesh, and all the information that I would have usually added to a subsequent fatigue calculation, I directly add to Nastran to directly calculate the fatigue life. So the advantage of that is, in some cases, our result falls are actually massively smaller because I don't need a frequency response analysis with every data point for everything for the whole analysis. I simply write out the life of every node at the end of the analysis. And this can be done, as I say, for transient analysis, for frequency response, random vibration, and so on. Okay, so it can be a lot faster than using classical methods where you have to get those intermediate results file, get that into fatigue software and calculate it. Just for reference, in Nastran, this embedded fatigue uses the same libraries and same methods that's available in CAE fatigue. It also uses the same licenses. So if you have a license to run CAE fatigue separately, you automatically have the same license available to run it inside of Nastran. So you don't need to get a separate license for that to work. And then a feature that's relatively recent and I think is underutilized by a lot of people is the concept of a module. If you ever used or know vaguely what a super element is, it makes it kind of hard to understand if you already know what a super element is, because at first glance it sounds like it's the same thing. It's not. So if you look at modules, it's simply a group of elements with its properties and everything, and I consider that the sub. But the advantage of this is I can now mirror this, not by physically moving the nodes. I simply say, well, I want a mirrored copy of that at that location. Nastran will internally translate the nodes, transfer material properties, everything as needed, and then solve it in the new location. In that process, it does not create new IDs because the results is now specific to a specific model. So even if these are part of the same model, they've got some unique IDs that says it's not the same model, they're just a reference, the same model. So this allows us to then quickly, if we realize there's a problem with this, I update this part and automatically after I rerun, it's fixed on both locations. So it's a very efficient way of doing sub-modeling or substructuring. What super elements does is an additional step where it actually calculates the simplified behavior of each of these parts, and then we combine the module. Even if it can do that, what we'll by default do is to simply not include the reduced or the simplified behavior. It can be a full nonlinear part. It's simply an additional copy. So think of it in a way like parts or instances in a kernel. Okay, so it's really good for people that have large projects that every one of the sub pieces is done by something else, and somebody else. It makes it just easier to then assemble it. And then we have the ability for Nastran to co-simulate with a lot of different software. Co-simulation is when it runs at the same time and information is exchanged. So if you look at this bottom example, that part there is there's some kind of a rubber component in this, but there's an air flowing from left to right. And the airflow changes the behavior of this part, and this part's movement changes the airflow. So this is great for cases where you cannot do a separately coupled to say, well, let's assume this is rigid, calculate the flow and map the pressures across. In this case, there's too much movement. Now, you cannot just couple with CFD. We can also couple it with atoms and a couple of other things. So just an example of what's happening in the background. So we've got our CFD model, we've got our structural model, and there's some kind of a mapping. The mesh is not the same. Elements, shapes, types, nothing matches. So if this is arguments like my CFD mesh, just a crude representation, my finite element mesh, that glue code in between have to take this information and find out what the pressure on every one of these elements are. The FEM software, on the other hand, calculates displacement, which is then passed back to this to get the deformed shape for the structure. There's some examples of simultaneous analysis, so it may not be that clear. You can see there's small amounts of movement at that location. So this is especially useful in Aero for the case where we do not have an infinitely stiff wing, for argument's sake, especially if we want to move towards a lower stiffness wing. So in that case, we don't need to model in the final state. We can model our actual wing, add gravity, all of that, and calculate the pressure, and we can see how that part moves. So this can, amongst other things, be used to calculate the Aero-elasticity, flutter, and whatever behavior of such a component. Okay, so in terms of Nastran and what it can do and kind of questions we ask, why you want to use it effectively. So for all of these examples, this is the kind of question I want to ask for which Nastran would be the answer. So in other words, can I build it? So does it fit? Not so much, but things like interference and so on. Is it durable enough? Will it fail? Is it safe? Can I test it? So is it possible to test, or can you do a virtual test on that? Will it perform well enough? Is it crash worthy or not? And why did it fail? So that's a common one we see is after failure reporting to try and find why something failed. Can it be lighter? So optimization. And even acoustics easy to load. So effectively, all of these we can do with Nastran specifically by combining all of these or allowing each of this kind of a question to be answered in single analysis. But this is because we can solve the large range of linear, nonlinear, even multidisciplinary problems. So if you look at these, it's just a pretty wide range of examples of things that's typically done with Nastran. Anything from rollover protection, crash simulations, plasticity, and so on. We can also link Nastran to Multiphysics, other software as well. So in this case, this could have been in theory an Adams model. So we're modeling all of the mechanisms and how the actuators work. But I want to see what the stress state of this would be. So I can export the information from Nastran and import in Adams to have that mesh, the displacement, the stiffnesses, and stresses to have all of those correct. Okay, now just to step back a little bit, this is kind of typical of how we do simulation. So we start with some kind of a CAD model, which is part of the CAD design phase, doesn't matter what you use. And that you will then convert after possibly cleaning up the model into some kind of a mesh and a model that we want to run. In Nastran's example, we could have used Pattern or Apex for the preprocessor. Nastran is simply the solver. Okay, and then whatever we set up, this is now where we run to find the structural behavior, durability, safety, dynamics, pretty much all of the things Nastran can do. And then afterwards, there will be a couple of loops typically, but then the next step will be starting the manufacturing process. And from Hexagon, it could have been HCAM and scanners, blah, blah, blah. It's all kinds of additional computer-aided manufacturing technology. And then finally, we have the final product ready to use or manufacture. In terms of the industries Nastran is typically used, these are just some of the examples. Anything from aero and automotive, consumer goods, speakers, musical instrument, guitars, and so on. Defense systems, electronics and cooling, vibrations as well in electronics, energy, heavy equipment, machinery, rail. So as you can see, quite a wide range again of applications that's possible to perform analysis we can perform with Nastran. Here's an interesting slide in terms of interesting and complex simulation that can be performed. Let's say we've got some kind of a composite. There's probably two cases that's relatively common. The one would be fiber layups, but the other one is what about fiber injected or injection molding? So in that case, we've got these short fibers typically with some kind of an interesting distribution, and I need to know what the stiffness contribution of that would be and the strength. So while Nastran's great at this, it can't really do this well. So there's a different product from the same group of products, so from MSC Digimat, which can microscopically model this and map that into equivalent properties that we can use in Nastran. And that can be done simultaneously. It can also be staggered, where we just calculate it and transfer it across and use it as a stiffness. But for the case where I want to see how this behaves as fibers arguments start to fail or the resin starts to fail, I can even include that into this simultaneous simulation where we microscopically and macroscopically solve the behavior for some kind of a structure at the same time. Some interesting quotes from customers. So Daimler Trucks. I'm going to read these, are pretty short. So MSC's robust offering of the Nastran Solver, continuous support from field team as well as continuous investment has made a significant difference in simplifying and speeding up durability analysis. For Husqvarna, they initially didn't do fatigue or didn't follow a specific process. So first, there was no clearly defined workflow for durability. So this changed when the Nastran embedded fatigue became available. So after a year of intensive evaluation, we decided to use the Nastran embedded fatigue in productive operation for operation analysis. From NASA, it's similar to that initial one, so I'm not going to add again. It's that same $10 million that it cost for a mistake. We have to retest. And that's just a test, not even redoing the design. For Bombardier, there's requirements for handling car bodies during operations, such as lifting stresses and some other international standards which they have to comply. So Nastran provides us with the opportunity to make sure the designs fulfill all the requirements before we start to make the first unit. For BMW, MSC Nastran's advanced optimization processes are used on both the component and system level to explore the design space. It plays an important role to capture the simulation process and accelerate the optimization schemes of the full vehicle. Correlation of the static wing load testing with MSC Nastran Nonlinear stress model was so accurate that at first I did not believe it. So in other words, it's actually possible to get really accurate results out of a finite element model if you're careful with how you set up your models. Okay, so in summary, in terms of Nastran, we've got all of these different, let's call it classes, for lack of a better term. It's the world's most widely used multidisciplinary finite element solver. when it comes to simulating stress, dynamics, or vibration on real-world problems. Even complex systems, it's the best and most trusted FEA software in the world. And MSC Nastran is an industry standard tool for computer-aided engineering for all types of structures, from deep sea to deep space. Interesting comment is that nearly every spacecraft, aircraft, and ground vehicle designed in the last 50 years has been at least partially analyzed using MSC Nastran. Okay, then the next section is now, we effectively now concluded the first bit in terms of what Nastran is, if you're not familiar with it. The second bit is there's two phases. The first one, I'm highlighting a very specific feature that's extremely useful in Solve 400. And then the last bit will be a bit in terms of development changes that was made in the last couple of years. Okay, so if you look at Solve 400, so that's for nonlinear implicit solving. In terms of development, it's been 15 years in the making. While solving it, we can run a series of different kinds of sub-analysis types, nonlinear, static, modal, buckling, all of those. So as you can see more, and some of the functionality of the advanced elements from Mark was added, the contact from Mark was initially added. At this point, it's now co-developed, so features in Nastran get sent to Mark and backwards as well. So the contact algorithms are very close to the same, making it easy to switch. Okay, so in other words, in one nonlinear analysis, I can model a sequence of events, which is why we can run different simulation types. Another way of saying it, simplest example, I've got a guitar string and I stretch it a little bit, and then I want to do a modal analysis. I want to stretch it a bit more, and I want to do a modal analysis. And by doing that in one analysis, I can get the different natural frequencies depending on the preload that I've applied. Also added some smart defaults, making it easier to set up the analysis. But this specific topic is about this little setting, the NL-perf, nonlinear performance setting, that became available recently. And there's a couple of improvements over the last release or two. Okay, so this is an example model where so it's 3 million degrees of freedom, 18 bodies, 54 body pairs. And we're looking at, if I look at that green one, NLS simply stands for classic nonlinear solution. And this NL-perf is the nonlinear performance module that does the same, just in a different way. If you look at the runtime for single CPU runtime went from 27,000 seconds to 18,000. Then as you increase it, you keep on seeing both decreasing time for both of these, but also better scaling for the newer method. So what the newer method in the background implemented is a couple of changes. Some of the most notable will be specific improvements to parallel processing of multiple elements, but also in terms of the solvers that's being used and other minor settings. Good. So other examples that MSC internally tested, so there's a really large set of models that was used. And this is just some examples by using blue again, the classical single CPU. This orange one is using 32 cores on a single machine, SMP shared memory parallel. This one machine with multiple cores. And then the same with the new settings. And you can see there's a significant drop in runtime, and then again for multi-cores also a significant improvement. Okay, in terms of changing it in Apex, it's really easy. You simply change to the high performance solution for Solve 400. That's it. Once you've done it, model is ready to run. Now, in addition to this, I want to pause a moment and rewind. So this is an example model where they're running the analysis, and there's additional files that can be output about the iterations, which then makes it possible to track how the iterations are going. So if I play this again, to run the simulation, and then they've got a standalone tool that you can plot how the iteration, the force conversions and displacement conversions, and so on, how this progresses over the analysis. So that makes it easier to track when and why things go. Okay. There's also a tool that was included in Apex. So there in the background, the model is running Nastran, and by using the VTK integration in Apex, it's possible to add stuff, and that was added in, so you can see the same kind of graphs while it's running. So once you're done, you can just clean this up again. So that helps as well. And then some quotes from customers. Had a model with a very large number of RB2 elements. Previously, it took 1 hour and 30 minutes. With the settings now 6 minutes. So that's one of the best improvements I've seen on this. It's looking good, about 50% of all the run times. One of the models is a 10 times speed up. Some very impressive runtime reductions, just add one parameter, and that's it. My own experience, I've recently worked on a nonlinear customer model for a support case, and just adding this parameter changed the runtime from just over 50 minutes to just over 20 minutes. So it was a bit over almost 2.5 times faster on the first test model that I tried this on. Okay, and then the last section I want to cover is for the last couple of releases. What has changed in Nastran? And please, this is by no means an exhaustive list. So for the first two, I added a section just on other improvements. For the later ones, I did not add this, as again, it would be a pretty long section. So I'm trying to highlight some of the most important features to some extent, or the most widely used set of features. Okay, so in 2018, there's an ability added in Nastran to automatically generate contact. So for a simple model where everything needs friction and everything is in contact, you can let Nastran figure out which elements are where, and you can even write out the information in terms of, again, these are my new contact bodies. Okay, so that's, I'd almost say, useful in a small subset of models, because often we have different material types, different friction coefficients, and that is not then possible to set because we don't initially have the bodies. But if it's a quick analysis where everything is the same material and same friction behavior, it's then relatively easy to set. You can also choose additional settings, whether it should be contact or glued contact. So you have a bit of control, but not on a per part kind of a level. On the other side, we've got modules. So that's the parts that I explained earlier. So it's a way to break down the model into individual components. And when you run it in parallel. IDs can overlap, which makes it a bit easier because everybody can work on its own and not worry about using the same IDs. In 2019, I need to go to the other improvements. So in addition, and there's more, there was improvements to topology optimization. It's possible to add just a command line option that says solve equals order. And if you look at Nastran, there's quite a few different solvers. The classic one, the full, is very capable, but not necessarily the fastest. There's also Paradiso solvers, MUMP solvers, CASI solvers, and so on. So what this does is, based on the features in your model and the size, it tries to figure out what's probably the most sensible kind of settings to use. It'll also activate things like multi-CPU. You can limit it and so you don't use too many, don't have enough licenses. We can also specify frequency-dependent material models. There's improvements to Rotordynamics. There's the concept of multiple mass configurations in one analysis. Previously was something similar, but this is expanding that significantly. There's lots of performance improvements and changes to the ACMS method. This is again for calculation of natural frequencies, typical of large models, lots of frequencies. It works really well. Okay, some improvements in 2019. So let's get to that one last. Polyelastic materials is a feature that's actually over quite a wide range of Nastran versions. That's it. There's improvements to this. In short, it's a way to model trims, so the plastic parts in a vehicle, without the typical approximation that's done in this industry. And this is typically used for acoustics. So it's to model the behavior of the plastics parts in let's say, a plane or a car and get the correct behavior by including those effects. It's also possible in Nastran, something that is not that clear. There's a couple of ways to model fluids in some kind of a simplified way. There's a virtual mass method, which is probably for large earthquake on something like a wall with water on the one side, up to using the same acoustic theory, but then using that to model the elements inside and to model the fluid and how it sloshes. Yes, you heard correctly, it's possible to do sloshing using that, but it's linearized, meaning no large displacement, no splashing, and so on. You can, in a Sol 700 simulation, which is Explicit Dynamics, do a full sloshing simulation if you really want to. But this is a very efficient way to couple fluids and structures. So if you want analysis, do both. And in this version, they change it so that you can do a real, in other words, a normal modal analysis to calculate both for heavy fluids, liquids in other words. While previously you would have needed to do a complex modal analysis because there's the results for the pressure is out of phase with the results of the structure. And now, in terms of other improvement examples, they've added ability or improved the ability to do nonlinear harmonic response. In other words, nonlinear frequency response. There's material models that was added to Sol 700, which wasn't available before. The improvements of Sol 200, in other words, optimization runs is improved. Random response analysis performance is improved. Again, improvements to that method to calculate lots of modes. Features was added to the modules, and again, since modules was added, every release or every couple of releases, there's significant changes and improvements. So more things you can do, easier to use, and so on. More composite failure material methods was used. Linear contact improvements. So just for reference, something that always bothers me. When you talk about linear contact, there's nothing linear about contact. It touches or it doesn't. And based on that, the behavior is dramatically different. When we talk about linear contact, it's actually a nonlinear analysis, but with the only nonlinearity being contact, whether it's in contact or not. So we assume no plasticity, no large strains, no large rotations, all of that. So just if the only nonlinear effect is contact, it's just a more efficient way of solving this. But there were some improvements to that in that version. Okay, now in the next couple, you won't see that additional section for additional options. So I'm just going to feature or focus on some of the specific features that I highlight here. So in this version, you can model imperfections in Sol 400. So you specify a separate card that says, I've got a mesh and I want to see what the effect is of a moving node, but I don't want to move the node. So by including that card, Nastran will then effectively move that node and solve it. And I can change just that one file, but I keep on using the same initial mesh for different initial imperfections. So I can do that to figure out what the effect would be of those initial imperfections on actual frequencies, stress states, and so on. We also specify frequency function of temperature for frequency-dependent materials. There's nonlinear buckling effects that we can model. 2021, the MUMPS solver. Nothing to do with the sickness MUMPS. So it stands for multifrontal, massively parallel, sparse direct solver. So let's stick with MUMPS. So it's a solver that's really efficient and it scales really well with number of cores, but previously was available for Sol 400s and nonlinear analysis only. And this is now added to linear statics as well. So that speeds up the run at the cost of increasing the memory usage a bit. So in Rotordynamics, there's some features that was added. You can have model bent rotors. You can get additional output. You can change spin speeds or specify different speeds for different motors or rotors. And so those for motors and rotors are the same thing. Okay, and then CA fatigue was added to Nastran, or at least improved. So they made it a bit easier to set up algorithm improvements by incorporating this. So it effectively runs fast. That's one of the most important bits for that specific version. It was already available before this. I can't remember when exactly it was added. In 2022, if you go to super element, so think of a super element as a module, but with some simplifications already calculated, the stiffness and the mass and so on, and is reduced to just the attachment points. So in this case, we can now use super elements with some machine learning inside, which you can then, let's say you specify a couple of different thicknesses for a plate and you want to see how that reduces. By using this feature, you can now calculate pretty much any thickness, what those properties should be, and it approximates. It's not an exact result, but it's a much faster and very quick way to do certain types of optimization. Yes, at the end you can go back and verify that that actually behaves as expected. It's a very fast way to do certain things. Then high frequency acoustics, we typically use what's called statistical energy analysis. So it's that last bit of the frequency behavior. And that was added and improved in Nastran in 2022. Another feature that was added and changed was the ability to model bolts using an easier way. There's always been lots of ways, but there's a very easy and clean way that was implemented in 2022, specifically for bolts in Solver. So it makes it a lot simpler then to define the bolts and to define the preloads. In 2023, modules, one of the changes was to have a separate output file for every one of my models. So that makes it a bit easier if you need to, let's say one person handles the doors, the other one the frame. From one analysis, just send the results back to the person of interest. So otherwise you would have had this massive result file that's shared by everyone. There's the ability to do only the peaks, the peak responses in the natural frequencies to then get the operational reflection shapes. So it makes it easier or faster to do these operational reflection shape result calculations. MUMPS again was added, but now to the Langsa solver. So the Langsa solver is used most commonly to calculate normal modes and buckling for normal sized models, not necessarily that one, whereas the ACMS method that's intended for really large numbers of modes and large models. As part of that, there's actually a static calculation that needs to be done a couple of times, and they've added the ability to use MUMPs. So effectively, by using this in a modal analysis or a buckling analysis, the runtime should effectively come down significantly. So in 2024, which is the last one here, because 2025 hasn't been released yet, we're at 2024.2, I think. So TPA, transfer path analysis, has to do with acoustics and where energy comes from and goes and so on. So it used to be separate calculations that you had to do to get to that final state. It's now possible to do that using a single analysis. It's then also possible to do better topology optimization. It's the same algorithms effectively and same method as used by generative design. So I'm changing from this to generative design. It's just one parameter change. And if you want to, you can add additional things like draft angles and so on. So you have a bit more control there. And then the last one, this one that we covered in the previous section, was spending some time and effort on tweaking Nastran to run faster. So activating this NL perf setting inside of Nastran was all for analysis. And that brings us then effectively to the end of the presentation. So thank you all for listening, and let me know if you have any questions.
Gerrit, you've got a question from Akash?
Yeah.
Akash?
Akash, you're muted. You're welcome to talk. else?
Okay, now is my
Yes, you can
audible
hear
now?
now.
Okay.
Yes, thanks, Akash.
Seems like my audio device is not functioning. I wanted to ask regarding the licensing for the fatigue module. So you're saying if we need to run a fatigue analysis, it's gonna draw the fatigue module. So we would actually need to have the what you call it, the licenses for fatigue, even though we're running it in Nastran.
Yes. So if you use tokens, fatigue, depending on the model, I think draws 25 or 15 tokens. Nastran Basics, linear statics is 113, I think. So if you run a fatigue analysis inside of Nastran, it's drawing both sets of licenses simultaneously. If you want to do it after the fact, then it'll only draw 13 for Nastran and later on 15 for fatigue argument. If you have a non-MSC one, in other words, a dedicated license specific to fatigue, then it's not going to matter. Then if you have a Nastran license and a fatigue license, the two will work together when you run a Nastran fatigue calculation.
Right. Is it 15 now? Because the last time I checked, it was something like what, 48 or so for fatigue.
If I remember correctly, and Zach, any of you can correct, but I think it's 15 for time domain, 25 for frequency domain, or 40 if you use some of the really special additional features, which isn't really fatigue based, but it's things like calculating whether two parts will interfere due to some kind of a random vibration. So effective interference in operation kind of calculations.
Right. Okay. No,
Yeah,
thanks.
got it. Just to confirm, the time is 15, frequency domain one is 25, and the premium one is 48 that you just mentioned, and the random one is 15. But I think between 15 and 25 you will do probably 80% of what's required.
Okay, no, thanks, Zach. Thanks, guys.
Pleasure, guys. Anybody else? If there's no other question, that then brings us to the end of the session. Thanks for attending, everyone.